Hey, good morning, everybody. It's 11 a.m. Pacific Daylight Time. My name is Jason Wampler. I'm the host. Another episode of the Rocket Minute. And there you go. Um, just still playing around with production right there. I like that better. Anyway, today we're continuing to work on our double-engined rocket here. I did something somewhat stylish, but again, I want to explain what I did. I cut angles in the bases of these motor tubes, so in one sense, it kind of evens up the overall flow and look of the rocket. In the other sense, it's going to create a challenge because these motors they twist on, so you have to keep them at a certain position to maintain the aesthetics. The other thing you'll notice is I did not cut this to be even with this one. Sometimes this stuff happens. You can be persnickety about it. The honest to goodness truth is sometimes things work out, sometimes they don't. We get out a couple of tools and we're going to go ahead and take care of that right now. Like I said, I'm in the process of reorganizing the studio. I gotta tell you, I really like the way this layout is working. I don't even need a stand. I've got clear shot, no stand. Unfortunately, you have to see my ugly self. But what I want you to see is what I'm doing. So we got 1, 2 lights on, plenty of natural light, daylight. I really need to shoot these videos in the morning with the natural light being blocked by the blinds, the overhead bedroom light, and the office light on as well. Although I'm kind of thinking that the office light might not actually be necessary. This is the upper portion of this rocket. One last design change I am thinking about before we get into this repair and the aesthetics. I am thinking about, and I think I will now that I'm kind of talking myself into it, because I can always buy another section of this for the other student rocket. I'm thinking about going ahead and machining this down. Remember we talked about that the other day. This looks like, shoot, I don't want to say, no, I don't know. I'm not really sure what that thickness is, but the thickness of the walls of this coupler is twice the thickness of the walls of this, but they're the same rough diameter. So what do? You remove half of the thickness of this coupler to have a press fit inside of this. The other, where you have about roughly 1/4 to 1/3 of the length, actually less than 1/3, a little bit over 3/8. Now, how much is that? That's too much. A little over 3/16, which is 1/16 over over 2/8, or 1/16 over 2/16 is 1/8. Never mind. I should know how to do math, but my brain is not completely warmed up. Either way, if these two are the same diameter, but this has a thicker wall, and this is a lesson on selecting your material for your couplings. Unfortunately, with using plastics, you're not going to find stuff that's automatically going to serve as a coupling for another material. Chances are you're going to have to either use a lathe and lathe it down to the precise inner diameter of the two pieces of material you're trying to couple, or you're going to have to use the old-fashioned method, which is my method, which is just sanding it down on a belt sander, either handheld belt sander or something that's affixed to the tabletop in a shop. But like I said, even if you get a coupler that's outer diameter is greater than the outer diameter, slightly greater than the outer, or even a lot greater than the outer diameter of the material you're trying to couple, it's the inner diameter of that coupler material that you're concerned with. If the inner diameter of the coupler material is smaller than the inner diameter of the material that you are trying to couple, then you can use it. anything with a greater diameter than the outer diameter of the material you're trying to couple, it's just going to be more work. But what you're really concerned with is removing material from this, half the material from this, the fit and the inner diameter of that, slip fit the press fit in, and do some calculations, do some strategy, because you want to know on all three sections of this rocket. That's the middle section. This is the upper section with a nose cone. You have to build things in sequence. And I've made this mistake too. So if you want this coupler and this section, well then guess what? That's going to limit the size, the diameter of the electronics and payload bay, which is what this rocket is going to have. This is going to be more of a sophisticated rocket build. We still have the single engine rocket. Don't worry about it. We're going to make that one a basic. But if you do that, then you can't slip anything in that's the inner diameter of this piece, because you got this coupler in the way, and in the back you got Gitz coupler in the way. So you might want to think about, just putting this into the end of the forward end. All this section is going to have, at the very most, is going to have an anchor spool with an eye bolt and a catch for the upper shock cord. Now if this rocket has three sections, it's going to have 4 shock cord halves and 2 parachutes. You don't necessarily need drogues, but if you do, you're going to have 2 drogues, 2 main parachutes, and 4 shock cord halves. That's going to add a lot of weight. However, all things being considered, this is a complex rocket build. You have all this area here for electronics. Now, placement of electronics in this is obviously not going to be side by side. They're going to be miniaturized. They're going to be one in front of the other. But the long length affords a lot of interior space, at least longitudinally. And so then this, of course, is the strongest coupling. It goes towards the back, because you don't want the rocket's fuselage to be broomsticking on launch and placing undue stress on the coupling. Notice the length of the coupling too, and how tight it fits. And of course the other thing, this is a complex rocket. It is taking us a long time to build. You want to recover it. The other thing that this area is going to accommodate is a recovery system, a dual-ended recovery system. And guess what? That's going to solve one problem, because we don't have to drag discharge pressure from the separation pellet, separation fuel pellet in the rocket motors. They're not going to have that. You're going to be putting black powder, GOEX FF black powder, very small amounts of, in caps, and behind cotton. And I'll show you how to make separation charge units. But out of sections of heavy-duty straws and electric matches. But you're going to need electronics for that, and it's going to have to be on both ends, because you have to separate this section to get the 2 shock cord halves, the 1 drogue and the 1 main parachute from this section. And for this section, it's going to be upper jump to this. Then you're going to need two. You're going to need a separation charge unit to push this off the top. And of course, it's going to be a double-ended. It'll be controlled by like, say, 1 event timer, but it's going to have 2 spouts, two actionable, 2 action or output spouts for either run, because you're going to want all 3 sections of the rocket to come apart, and to like I said, to deploy the 2 parachutes and the 2 drogues. 2 parachutes and 2 drogues are in between 3 sections, of course. So it's just basic physics and simple math. So, and we're going to work on this coupling as well, machining that down. We talked about that. So let's talk about what this is going to have. Guys, if you want to get really fancy, I don't even know how to do this, but if you want to get real fancy, get a miniaturized camera and mount it on the outside, or cut a through hole and secure a camera from the inside out. You can mount a downward facing camera. You can even get 2 cameras to balance out the rocket, but that would be a real tight fit. In addition to the fact that you're going to have the anchor spool with eye bolts and Mountaineer's miniature safety clip, plus the upper shock cord half for this particular section of recovery system. So this section is going to get really, really crowded and really heavy. Not to mention the fact that we're still working on the technology for the nose cone. And the nose cone, I want it to be elongated and pointed. I want it to be roughly about 3.5 inches long. Now, if I wanted it solid, that would solve the problem of not having to add weights to the nose cone to get our center of pressure correct. But then again, I don't know how heavy to make the nose cone because we haven't completed assembling this rocket, so we don't know where to put the center of pressure. And again, I don't even I can't come up with the calculations. I can give you a rough idea about center of gravity. I mean, I always balance the rockets on the forward end of the bottom 1/3 section of the rocket, the bottom 1/3 total length of the rocket. But again, that's changing too because I'm adding this. And as far as weight is concerned, weight distribution throughout the rocket is going to contribute to the variables of the math equation for calculating the center of pressure. Okay, so this thing needs to be fully loaded. So we are kind of starting off on a complex build. I'm very excited about it, but unfortunately, folks, two things about rocketry. The bigger and badass, the bigger and more badass the rocket, the more complex it becomes exponentially. You have to hand it to people like Rocket Lab, Blue Origin, and SpaceX. I think, I got to be honest with you. I think Elon Musk is a very, very intelligent person, and he surrounds himself with very talented people. Jeff Bezos and Blue Origin, I think you guys are doing great things. Rocket Lab, you guys are doing great things too, because I'm coming to understand if you just had one person building a 10-story rocket, I mean, technically speaking, I could do that too, but it would take me a lifetime. I would probably be 150 years old before I got it done because it's so labor intensive and there are so many things to do. In fact, I probably couldn't. I could build maybe like a 5-story rocket by myself. That would take me probably about 10 years because there's so much labor intensive work involved. There's stress analysis and calculations. There is some computer analysis and math involved. And the larger you get, you want to make sure that your rocket's going to hold up structurally. I'm kind of bouncing all over the place with subjects. So later on today, I'm going to machine this down myself. I'm not going to do it in front of you because machining down these couplings generates a tremendous amount of PVC dust and waste. I'm trying to think if I could just do that outside. I have a power inverter and take my belt sander and just go outside and shave the living daylights out of it. This alone, to get this coupler to where it can fit snugly in this upper section, doing it the way I do it. If I had a $750 miniature lathe like the ones they have at Harbor Freight, I could probably get it done in about less than 10 minutes, probably like 15 or 20 minutes, 10 minutes of setup and 10 minutes of work. And that's it. But since I'm standing on a belt sander, I got to really lay into that belt sander, keep the engine running, turn the inverter on, fill the car up with gas to make sure it doesn't run out of gas. And it's probably going to end up taking me about 30 or 40 minutes, possibly even up to an hour, because the belt sanding down the material off the outer diameter of this so it'll fit into the inner diameter of this, which is where I want it to go. It's just labor intensive. Another thing, folks, I just want to mention too, anytime and every time and anytime at all possible, you have the resources to actually set up a shop and find a tool that will make what I'm instructing you on how to do easier and faster. Do two things. Jump on the opportunity. Go on Craigslist, find tools for sale, look through free stuff, set up your own shop. Okay? Number one. Number two, hit the like button, hit the subscribe button, and for goodness sake, leave comments and give me some data and feedback on where you got this equipment and what tools you got or what tools you made or invented that make these jobs easier. I'm just the boys and girls, or girls and boys. I'm just one person. It's just me right now. I have to generate some income off the channel. I'm working on another income source maybe coming in tomorrow, the 10th. I'm really excited, but I'm really stressed out about that. I'm working on a government grant, aviation research, and I've got a bunch of stuff that I can sell for cash too. But the God's honest truth is, I need more resources. Unfortunately, I'm limited by a lack of resources. But if in the comment section, if you can tell me something about maybe what I'm doing wrong, or maybe there's an easy way to do things, as in less time, less money, please leave a comment. I may come across like I don't know what I'm doing. Sometimes I don't. Sometimes I'm making mistakes. Guys, if somebody criticizes me or even chews me out, the concept of that is, you learn from other people's criticism. If they criticize you, don't take it personally, especially if you're trying to build rockets correctly. Don't take any criticism you get from other people personally. Don't take it like they're trying to hurt your feelings. In a way, they're actually trying to help you, and I need that help. So hit the like, hit the subscribe. I'm gonna make every attempt to monetize my YouTube channel. Keep it clean. Not cuss words, which I kind of let that slip about 10 minutes ago. We're not doing anything to weaponize anything. We do launch vehicles, micro launch vehicles. We do sounding rockets. We do sport rockets. Sounding rockets are sampling the atmosphere, geological survey, anything and everything for data, for micro launch vehicles, or for sport and recreation and education. Education is key. The more you know, the more empowered you are. So anyway, I'm going to do that later on today. But what we're going to do, and I'm just going to kind of put this in here for now. What we're going to do is cut this bad boy loose, and then we're going to make a little bit of noise. But here's the other thing we're going to do. There's an old saying, an American saying, I believe, carpenters have long maintained one credo, not only, but one of the most important credos of a carpenter is measure twice, cut once. So make sure of what you're doing, because if you reduce the size of a part or a material and you go too far, you have to reduce the other size of the other material to match. Now, once you reduce the size or volume of something, you can't undo that. If you cut something too long, then you're safe. You can cut it shorter to match the other part, or do what needs to be done according to the job requirements. You cut something too short, either you match the other part to it, or you throw the short part out. Use it for scrap. Or if it's too short for anything, well, guess what? You have to throw it in the trash. You can't. There's no other use for it. So measure twice, cut once. In that regard, I kind of put my glasses on and off because I can't see with or without them. I have 2 black markers and 1 red marker. So this time I've actually gone overboard. Before we do anything, we're gonna go ahead and okay. So I just kind of put those 2 together. Before we do anything, this is a lawn mower. It's kind of a similar concept to balancing engine parts. When you're balancing a Chevy 350, you start with the piston, pin clip, rings, connecting rod with bearing shells. You put the whole assembly together, and you start weighing each one of those piston and rod assemblies, all 8 of them. The 3 Chevy 350s, an 8-cylinder engine, 8 piston, 8-cylinder engine, and from there, because of the concept, you can't add weight to something that's too light. You record the piston and rod assembly with the lightest weight, and you make the other 7 connecting rod and piston assemblies weigh exactly as much as the lightest rod. So it's because it's possible, according to the laws of physics, to remove material than it is to add. You can add material in some instances in engine rebuilding, but it's such a headache. It's worse than being an underpaid engineer. So the point is, with balancing things, you use the lightest part, and you remove material from the other parts that are heavier than the lightest part to make all the other the parts match the lightest part, balance things out. Similar concept on rockets. Not everything's going to be absolutely exact, especially when you're scratch building rockets, but I know you can do it. But on scratch building rockets and the motor tubes, sometimes even out the pant legs and an LC 8P, which is an 8-engine rocket, which we can build, but that's not going to be for a year or 2. Then of course you're going to have to use precision materials. But with an 8-engine rocket, I built one of those before, and I noticed one thing for true is that you have to, before you install the motor tubes or anything else, you got to match. You got to cut 8 sections, and you got to match all 8 sections up to each other as best as you can. Using math is not a savior. CNC machining, it might work out. But if you stack those motor tubes top end on end, and you run your finger along the top of them, and you're expecting to feel a flat plane, I've got news for you. You're just not going to. So, you know, you got to deal with that. So perfect is good enough, but sometimes it's impossible. Good and excellent are a lot more feasible. But for the sake of aesthetics, like in this case, we can see that this angle is above that angle. So I'm going to mark it where I think it needs to be cut so that this motor tube, removable motor tube, is as close to the shorter one as possible. So I'm going to go straight across the tip of this, and I'll mark that there, and that, you know, and that's going to correspond to another tip down there. And guess what? That's the angle at which I'm going to cut. Oh, I got another thing on the angle. You got to match the bottom angled edge. Go straight across and match the bottom angled edge of that too. So it looks like this angle is steeper than that angle, which is an optical illusion. This one's higher, so this looks like a steeper angle. But you know what, folks? It's not critical. It's not going to affect the stability of the flight of this rocket. So I've got the 2 points. When you're cutting these too, because these engines twist on, you twist them till they stop before you cut these angles, and you put marks on them. 1 and 1 dot slice, or 1 dot line here, 1 dot line there, and that's the 1 dot motor housing, the 1 dot upper motor housing right here. That goes together, and 2 and 2. Not only that, 1 mark on top of the other between the 2 parts that are separable, and that's after you've rolled these motors in place firmly, but not so tight you can't loosen them and remove them after a single flight. And remember, you're going to have to keep doing this. I just remembered I'm going to have to keep doing this because these are going to be single-use motors. One other thing I want to mention, actually, let's see the one. Okay, so here we go. We're going to take this guy off. One other thing I wanted to mention, I told you that I was going to go on a McMaster Car website. I downloaded their app on my phone, and they're absolutely, positively just as spectacular as I remember them when I was doing business with them nearly 5 or 6 years ago. I do believe I owe an outstanding invoice to them, so I've got to get that caught up with. But one thing I wanted, and this is where you're going to need a dial caliper. Remember what I said about getting a tube for coupler? Well, I'm getting what's called Garolite triple X. There's Garolite double X. There's Garolite triple X. Garolite triple X is a lot more expensive than Garolite double X. Garolite double X has a very, very strong advantage over other materials in that it can house a tremendous amount of pressure and heat. It's not that it's made out of plastic. I'm not entirely sure what does make up Garolite. I believe it's a combination of carbon fiber powder, maybe mixed with a little bit of ABS and some carbon fiber matting thrown in between, and maybe a little bit of rubberized polymer to bind it. But I'm not a chemical engineer. I don't make raw materials, so I'm not absolutely sure. Garolite double X on McMaster Car, a 24-inch section that's 1 inch in diameter with a wall thickness of what we need, which is not 1/8, but possibly 1/4. No, I was dealing with 1/16 to 1/8. A 24-inch length, 1 inch outer diameter, 1/8 wall thickness, which in total is 1/4. So 1/4 off 1 inch leaves 3/4 in diameter. No, that's not right. Excuse me. 7/8 in inner diameter. The 7/8 inner diameter fits evenly between the how I say it, that measurement fits evenly between the outer diameter of the piece. So you 7/8 is 1/8, so you split 1/8 in half. That's 1/16 wall thickness on both sides. So let's start with the wall thickness of that Garolite double X. The wall thickness, 1/16 wall thickness, 24 inch section, 1 inch in diameter, and 1/16 wall thickness would be a total of 1/8, which would mean it'd be 7/8 inner diameter. That would run you about roughly $25 plus shipping from McMaster Car. Now that stuff is okay, depending on how much and how long you want the motor to burn. I believe that might actually be the same stuff that Aerotech uses for their single-use motors. However, again, it's a 24 inch section, 1 inch in diameter, with a total 7/8 internal diameter, wall thickness. 1/8 divided by 2 is 1/16. Again, $26. Maybe a part that small. Maybe McMaster Car can float you the shipping, or maybe they're going to charge you about $5. So just plan on spending something like $30 plus shipping. However, here's the catch: 1/16 wall thickness, Garolite double F. That's two strikes. Number one, not 1/8, 1/16, 1/16 wall thickness, and it's only Garolite double X. That's a really thin walled material. So you're gonna only be able to use a motor with a total burn time. I'm not talking about total impulse. You'll only be able to use a motor with a total burn time of less than 4 seconds before the walls of that Garolite double X tube start to compromise. You don't want your motor tube looking like a hot dog. The fact that you've got this outer PVC tubing is fine. The fact that it's a single-use motor is fine. So maybe factoring that in, maybe you can add a couple seconds. Maybe you can add about 3 seconds, so 3 plus 4. I'll give you a 7-second burn time, which is a long time, but that'll get you between 5 to 7,500 feet, maybe, depending on your power to weight ratio, coefficient of drag, and the type of dry fuel propellant you're using. So you got to figure all this out. So when selecting materials for your single-use motor, you got to figure out several things, and this is where it gets complicated. First of all, is your rocket going to have payload bay electronics with its own independent dual separation recovery system? If not, your rebuildable motor doesn't need an ejection charge at the end of the fuel grains with that's integrated by design into the bulkhead closure. The forward end of the motor. Second of all, is it a multi-engine rocket? So if it's a multi-engine rocket, we'll talk about nozzle design, but that gets very complex. I figured something out about vectored nozzles, fixed position vectored nozzles, like the ones on one of my favorite rockets, the Titan 6, if I'm calling it that. And I figured out what the method to their madness for vectoring those main nozzles at a very steep, almost 40-degree angle, 40-degree angle relative to a transverse straight axis at the bottom of the rocket. However, where it meets up at the center line of the rocket itself, that point, that apex between the two nozzles, that section, you take a measurement of that section where those two vectored nozzle imaginary lines meet the center line of the rocket, take that all the way up to the tip of the rocket, again, factor in total impulse, coefficient of drag, center of pressure, even center of gravity, and then from there you can, actually I shouldn't say center of pressure, it's center of gravity, coefficient of drag, total impulse. Then from there you can figure on your center of pressure. But between the point where those two imaginary lines of the vector nozzles, the angles of those main vector nozzles, the bottom of the motors meet, that's the point you start calculating for section by section, the total length of the rocket from its tip to that section. That's when you use to section those, calculate this, run that calculation from Mike's Inventions. That's a website that has the nice young mathematician, I think with a PhD, real smart kid, less than half my age. He takes the rocket vehicle section by section, you run the calculation, you get all those calculations from each section of the rocket, put it together, you get the center of gravity. Well, that starting point is the angle at the apex of the angle at the base of the rocket where those two vector nozzles aim towards each other and meet at the center line of the rocket. And then that from the tip of the rocket, you section it, run the formulas, and you come up with the center of pressure. I think. But again, since and if I'm getting the name of the rocket right, correct, the Titan 6 was a marvelous looking rocket. Unfortunately, had that major failure that I already diagnosed and we talked about earlier. Two engine rockets, they're very, very difficult to make work. They have, for example, using my rocket, or the rocket that we're building together, it's ours, with a two section, with a two thrusting motors, remember, you have when a rocket's vertical, it's in vertical powered flight, which is a particular section of a model rocket's flight. There's powered flight, there's coasting, there's apogee, and there's descent, and then there's recovery. Those are the separate different sections of a model rocket's flight path. But with this motor attached, under powered flight, before it enters into coast, you have thrust on one plane. Remember that there's two different axes, two major axes. There's A and B that run at a right angle relative to each other, transverse, flat plane, right angle, but intersect at the imaginary center line, long axis of the rocket. But you've got major thrust that will control this axis here, because these guys favor one side or the other of this flat plane going through the imaginary center line, long axis of the rocket's fuselage, but you have nothing here. You have nothing to control here. So guess what? If you have those fixed angle rocket nozzles, how in the world are you going to control the other axis? That's what makes twin engine rockets very, very difficult to design, and they're just rocket engineers and designers, they finally gave up. They went with they took the example of the tragedy of the Titan 6, its last disastrous flight, which literally was a CATO, C-A-T-O, catastrophic motor failure. And they said, we give up. Twin engine rockets are just too much trouble, so we're going to go to multi-engine rockets. The Atlas, of course, used past tense 3 rockets in on the same plane. Basically had the same problem, but instead of having just 2 engines, it had another engine in the middle. So you have all the control in the world on the A axis, but the B axis you had no control. That's what I think. That's why I think they had so many problems with the Atlas rocket. I think it was a worst idea of all time, and all they had to do is just make, for lack of a better word, they could have been with a triangular pattern placement of those rocket nozzles with intermediate rocket and rocket exhaust, where how do I say it, unused energy from the combustion chamber would be in between the two rocket motors itself. You have a triangle of exhaust and a triangle of main rocket nozzles. And frankly, you could make that into one engine with one very large combustion chamber to control all 3 rockets, and a 1 turbo pump, and a fuel tank, and an oxidizer tank. And NASA could have solved every single one of those Atlas flight control issues and problems. But, I wasn't there. That was back in the late 50s. I wasn't born until 1970. It would be nice to travel back in time and put in my 2 bits worth, and tell them, hey, look, putting all the nozzles on one flat plane, you have control of one axis, but you don't have control of another. And those nozzles weren't gimbaled either. They wouldn't move back and forth. And even if they were, how in the world are you can control roll? You have the one constant in the middle. But like I said, it's just much easier to just make one engine with 3 nozzles and in a triangular pattern, 3 exhausts in a triangular pattern, in between that larger triangular pattern, and same thing as a 3-finned rocket. I don't like 3-finned rockets because it's hard. I just don't like the way they look, and but it's really hard to set fins at a 120-degree angle apart from each other. I'm not that good, so I steer away from them. But 3-finned rockets are incredibly stable. Three engine rockets, or one engine, one liquid rocket motor with 3 nozzles in a triangular pattern would be incredibly stable. You got 360-degree control. Now you don't need to control on 2 axis. just as long as you have an A and B axis, that's a minimum for control at the transverse base of the rocket and its business end. But I mean, you can have 8-axis control. You can have, but if you have 3 engines, you want multiples of 3. So you can have 1, 2, 3. You have 3-axis control that'll go through all 3 motors, and a 3-axis control rocket. I mean, you can twist and gimbal, and you can corkscrew that rocket, get around upper atmosphere turbulence, and get that rocket up to speed, 18,500 miles an hour, and get it into the atmosphere. Manual control override, automatic control override from telemetry from Houston, control in Houston, or in Fort Lauderdale, Florida, whichever you prefer. I don't know how it works. I think Fort Lauderdale, Florida, but 3-axis, 6-axis. If you want to get really fancy, 9-axis, 12-axis for a three nozzle rocket, or in a triangular pattern, a 3-motor rocket in a triangular pattern. Wow, 12-axis, 15-axis. I mean, you could get so fine-tuned with gimbaled nozzles, with variable nozzlets, variable bell profile on the exhaust nozzles themselves, and they can gimbal. All 3 of them can gimbal on 15 different axes. You can have a rocket that's so perfectly maneuverable and controlled. You can still have percussion and an imbalance in almost any section and length of the rocket, which occurs either in the fuel tanks or in the cargo bay. That's happened before, and you can correct that and compensate for that either manually or automatically, and you can still get that rocket in the atmosphere without the dumb thing disintegrating at 18,500 miles an hour. So there you go. But understanding the principles of how a rocket works and how it maneuvers, it's simple, but it's kind of an alien concept to people who don't understand or don't want to, have no interest in rocketry and rocket science. Again, I'm choosing the path much less traveled by developing a 2-engine rocket. I could build a 3-engine solid fuel rocket. We might attempt doing that, but the honest to goodness truth is, right now I kind of really don't have the heart for that. I've still got my level 2 rocket that I'm working on. I haven't been getting to that lately because it's kind of more important than I get viewers. My viewers, I mean, I'm a little under, I'm a little under 1,000 views. So I'm hoping that I'm getting YouTube's attention. Hey, and I want to tell YouTube, I think you guys are absolutely phenomenal, fantastic. When I get the revenue generated, I'm in this for the rest of my life. You're going to see more comprehensive studio. I'll get more people involved in production value. Of course, I think I probably need to lose some weight too. I'm serious about that. But anyway, we discussed a little bit of rocket science. So now that I've got this marked at these 2 different spots, I want to go ahead and visualize, put this down next to this one. Now look at that. I'm putting this right next to that, and I'm noticing that this angle on this end is actually steeper than the angle on this one. So I'm thinking, and look at that, I already got it corrected. Got these 2 little red dots, and this red dot is closer to the surface than this is. So that's gonna lower the angle. That's not just gonna even up the set length of this motor in that position on the rocket. It's going to make the angle a little bit shallower relative to the long axis, imaginary long axis of this actual rebuildable, not rebuildable, single-use motor tube itself. Okay, I want to talk about your options for Garolite triple F or triple X. I'm thinking of GoX black powder. Garolite triple X. But let's get this done because I'm doing a lot of talking. Get that set up to 6. Let's just do adjustment number 4. Plug your ears. Uh-oh. You know what would really help? Instead of plugging your ears, plug the tool in. And this is better too because I'm closer to the plug. Oh, what a wonderful day this has been. I guess if I behave myself, I get away with murder. Anyway, all right, here we go. One other thing too, I'm picking a seam of this table, line up this plane, the angle in the table. The other thing is this needs to be a dead right angle cut for imaginary straight line going through the ovoid shape because we're cutting the tube at an angle, right angled line, slightly shallower angle to match the angle of the other motor tube. We're just doing this for aesthetics. It's not absolutely critical to the flight of the rocket, but just roll it until you eyeball it and you can see, but be careful because you can fool yourself. Hang your head down directly over the line. Do the best you can. Oh, okay, so here we go. Okay, so that went well. The number 4 setting on this Warrior variable speed oscillating multi-tool is the best. I've got a new trash can too. It's a stainless steel trash can with a top on it. Matches the table, matches general industrial design and everything else. So we're gonna pick the crumbs and crusties out of this. I've got the little tool for that too. Some of these tools are really expensive, but you know, I'm thinking because these places know these individual retail outlets. Oh, there it is right there. You can see that. McFadden's hardware is fantastic, but this is a deburring tool. You can't get this at, like, say, Lowe's Hardware or Home Depot or Crown Ace Hardware or any other hardware store. This is like a machinist quality tool. This is for somebody who does this professionally. I build rockets professionally, obviously. So you're going to have to kind of look around for these things. If you're not in the state of California, I kind of don't know what to tell you. Even Harbor Freight does not have deburring tools, although it would probably be a good idea if they carried it. Just kind of get the little excess piece of plastic. When you go around the outer edge, just be kind of careful. This is more for dragging along the inner edge. So there you go. So there's that. Okay, so just all right. There we go. Now, the moment of truth. Let's match up the angle. Okay, with the other one. Well, no, still a little bit too steep. That's off by roughly about 1.5 millimeters. But you know what? This is for aesthetics. It is not for performance or flight control or etc. I should say flight control. There's nothing controlling the flight. You light the candle and you let the dang thing go where you want it to. So let's roll this on and see how well I even up the pant legs. Okay, so, and what do we got? Well, you know what? It's still a little too high. So, but at this point in time, instead of using the oscillating multi-tool, I got one more plug-in left, and I've got the cabinet full of tools here. And I kind of wanted to use this guy anyway. What I'm going to do is use the block sander, kind of take it down the rest of the way. I am sort of anal retentive about this. I want it to look better than this. And I need to sand up the end of this too. Again, folks, when you're building multi-engine rockets, which is what we're doing now, and we're doing a very difficult one. When we're doing multi-engine rockets, and you do removable single-use motors, this particular design, which I think is an incredible design. I got the idea from another gentleman, and there goes that zip tie. Disappeared into oblivion. You'll see a vacuum cleaner something to pick that up. I'm working on top of carpet right now, and it's anyway. Okay, so this guy, I just loaded up this new section of sandpaper. Here we go. Oh my God! Oh, there it is. And that stupid zip tie popped all the way over there. Can't control everything all the time. Okay, so here we go. Let me use a straight edge to figure out exactly how much I need to remove. Well, not too bad, but okay. Well, I'm not gonna squawk too much. It was off by a good 3/16 of an inch. So I go back and forth between millimeters and imperial measurements. And I apologize for that too. So I can also change the angle too, because the angle on this is still too steep. Now I want to show you how I'm going to do that. I want to tell you a little story about something called the Blackbird. I built that rocket a long time ago. I believe I've talked about it on previous episodes of the Rocket Minute. And I don't know how I did it, but back in the heady days when I first started building my own rockets, I'm telling you, my reach exceeded my grasp. But anyway, let me visualize the angle this is at. No. Okay. What I'm going to do, I'm going to shorten this up at an angle. But I'm going to shorten up the angle, and the less material is going to be taken off down here. I'm actually going to maybe start to drop the angle by about roughly 1 to 1.5 degrees at this tip here, and even up the pan like that way, because this angle is still a little too steep relative to the imaginary center line, long axis of this single-use motor tube. So, like I said, I'm going to start sanding and putting more pressure on the top to lower the angle, and that'll also reduce the overall length as well at this tip, and the angle this will equal the angle of that, just for aesthetics. The ironic thing is, unless I use one of these as a stencil, these are single-use motors. Um, you know, uh, these once these go through one use, I'm gonna have to replace them. So I'm spending a lot of time making these look real pretty, and they're going to only last for one flight, which leads me to believe another thing. I'm kind of engineering things on the fly right now. It leads me to believe it might be a good idea to go back to my original design concept of using aluminum tubes, and then making these Garolite double X sleeves, making them the part of the motor that gets shucked out of the aluminum housing. If I'm going to put this much effort into making these things aesthetically pleasing, and only last for one launch, then maybe I should make them reloadable. Yeah, so hey guys, I'm not perfect. If I was, I could walk on water. Okay, so here's the plan. And then I need to go ahead and clean up this guy too. But here's the plan. So we're going to sand, we're going to push down the top here and kind of lower that angle a little bit. You can see the space right here. So here we go. Okay, so now shush. One thing I should have that I'm going to start looking for, but I don't have the funds for right now, is a shop vac. That would really, really help. Of course, I kind of had one with all the vacuum attachments for that vacuum cleaner, and I got rid of them, so I don't know why the hell I did that. And now that I think about it, I need that stuff. My Uncle Dan would be laughing at me right now. He passed away, I'm sorry to say. So let me look at the angle. Okay, roll, flat pane, roll. Oh, look at that. Okay, it's almost the same, it's just a little rounded. Want more flat in the middle. It's going to throw off things visually. One other thought I'm having, maybe you can use the PVC casing, and maybe we can talk about Garolite triple X inserts for the reloadable portion of the motor, and make this a reloadable motor. Um, and the more I think about that, either that or the aluminum casing, um, honest to goodness truth is these are a lot of work. So, so I'm actually making a decision to fly. I'm kind of thinking it maybe, and then I went to a great deal of length to time these and mark these, and I've already got markings on the upper sections of the motors. Um, so when we make these reloadable motors, then I guess what we're going to go ahead and do is the inserts will actually be the portion of the motor that is single use and replaceable, including an integrated bulkhead and nozzle. And okay, and there's material for that too. There's glass, there's fiberglass, there's G10, which is perfect for nozzles. There's also bulkhead and nozzle material. Durham's water putty. Rocky says a really weird looking weightlifting guy on a container. You know, it's just kind of weird the way he looks. Rocky says, I just stay away from a guy like Rocky. Maybe he appreciates men too much. I'm sorry. I shouldn't really say that, but it just looks weird. Um, I should not have said that. I'm sorry. So, and I'm timing these. So, we're going to go ahead. Let's just go ahead and assume we're going to go ahead and make these rebuildable motor sections. And we're going to use, let's talk about Garolite Triple X. Garolite Triple X obviously is going to be stronger than Garolite Double X. So we'll make the entire motor section out of that, including the bulkhead with the delay grain already glued in place, the motor the fuel segments itself inside, and the single-use nozzle, whatever design that nozzle is, glued in place as well. And that will be, you know, we just take these out, push that motor unit out, that used motor casing and propellant casing and single-use nozzle and bulkhead out, and just put another one in. So anyway, so here we go. So yeah, let me just roll this up. Let's see where we're at and see if we were able to get things even. Guys, again, I know you may, I'm not entirely sure, if people watching this video are following everything, and I understand, yeah, that's good enough. Yeah, I'm not even sure, my target audience, if they're going to have, if they're going to even have the patience, the attention span to watch these. But, um, to make things exciting, I am considering that, to make things exciting. This rocket will launch. Eventually, we're going to get it to the point where we can launch it. And we're going to film some episodes on site and show that. I'm seeing more and more people do independent launches aside from, like NAR or AAA sponsored launches. The problem with doing an independent launch is not necessarily the fact that you're breaking the law, although you kind of are. The problem is if something goes wrong and you burn down some plant life, or you displace some indigenous wildlife, or if you hurt yourself or your own property, um, you're not covered. So you're kind of hanging your butt out, and there's no insurance company in the world is going to cover property damage to your vehicle. When you tell them, well, I was launching an experimental rocket, and the rocket went through the roof of the engine hood and took out the ignition system. So you tell that to an insurance agent, the one who handles or the agent handling your claim and your car's insurance company, and they're going to look at you and they'll say, I have to talk to my manager about this. And you'll hear the manager and then your agent talking, and he'll come back, the crestfallen look on his face, he'll be shaking his head and going, no, we don't cover that. So, if you're going to launch independently, keep in mind several things. Sponsored launches by NAR AAA, the den mothers of those particular sponsored launches, they've been trained and educated on how to handle disasters, how to handle accidents, how to handle injuries, property damage, how to handle disagreements, explosions. They've been trained in hazardous material handling and a proper maintenance and storage of equipment. So, like my friend Martin, who's the head of SCRA, chapter of National Association of Rocketry, sent me an informative letter. He lives in Fullerton as well. He's been trained in all that, so he knows just how to do things. And NARA and AAA have been around long enough. They're two rocketry organizations. They developed a set of rules that, if you obey them, you're gonna decrease the chance of an accident that you can't recover from to nearly zero. And there are assured events too. National Association of Rocketry. You remember, you go to their launches, you're insured for up to $150,000. How much the insurance liability is, but they carry insurance. NAR sponsored events, AAA sponsored events. You obey the rules. You have a membership, but you're insured. You're covered in case anything really, really bad happens to you or your vehicle. You're covered because they have insurance. If you go on an independent launch, again, good luck. If you have good medical insurance, that's fine, but damage to your hands, severe burns. If you're alone or with somebody, maybe with a couple of minors who don't have driver's license, don't know how to drive a car, maybe you're out of range for cell phone service, I don't know what to tell you. Because if something takes place, something really bad happens, you're simply not going to be around other people who are trained to handle that type of scenario, and you're not in the event is not insured. So be really careful and keep that in mind. It's best to go to a sponsored launch and be a member of NAR or AAA, just for safekeeping, and just safety for yourself, of course, is paramount. So we're gonna set these loose in here. Okay, so let's see what we did. We didn't do much, but there's that. Now, here's what I'm kind of worried about as well. The difference between this rocket and student number one rocket, and remember, as we discussed, these are not inner tube type or insertion type motor casings. They just mount externally like this, which means the strength that the forward end thrust this engine pushes on this upper tube, which is connected to the intermediate body tube, and that's of course connected to the upper tube. And then this rocket's going to have three sections. Well, all the stress is going to be on this MPT threading right down here. So I'm thinking, again, I'm just thinking out loud. I know I'm engineering stuff on the fly. I'm thinking that since these motors are not going to have a forward separation charge, that we can actually block the head ends of these. But what we're going to have to do, and you might not like this, is we're going to have to find a tapered cheese head machine screw and fastening system for the other side. And we're going to have to run a machine screw through 1, 2, 3 of these tubes after you've got them, after you've got the motors installed properly and timed. The good news about that is that keeps these motors from doing this. That keeps these motors from broomsticking back and forth. Multi-stage rockets that people use craft paper body tubes on, you can, downward facing rocket or downward facing camera, sees the thing flapping back and forth like an English chimney, like a chimney in London. And I don't like that. I don't like staging either. I've never been a fan of it. But these motors, under full power, the rockets under full power, these motors are thrusting. They're just pushing on that this one fastened area. There's nothing to keep them from broomsticking around on flight. So the way we're going to fix that is we're going to drill a hole through here, countersink it, that'll correspond with a hole through here and a hole through there, and the side is going to, you have one bolt going through all three, 1, 2, 3, not very tight, but just enough to keep these guys from toggling like this and transferring all that thrust pressure to these to this joint right here, because that's just plastic. That's just an MBT pipe thread. And furthermore, these sections of black, they've been machined down, so when you remove material, the part becomes weaker. So we're going to do that. I figured on doing that. It's a basic, simple fix, but I want you guys to see how I do it after I've done it successfully. I'm going to attempt it, and when I've done it successfully, then I'll share that with you. Of course, we're going to put it far enough where we have a reasonable length or section of motor with a grain segment in it. So that's pretty much that. So you have that to look forward to. I know I do a lot of talking people. I know there's a lot of lecture. I'm thinking about getting a dry erase board and drawing down pictures, writing down and drawing pictures of what I'm talking about. I'm not an illustrator. My handwriting is absolutely, it's just beyond terrible. I mean, doctors with their handwriting laugh at me. So we'll figure that out as well. I need somebody with better handwriting. I have more money, dry erase board behind me, so we can do lecture and lab. I can just turn around because the camera is going to stay here. The actual mount for the camera is double-sided tape, the inside surface of my door. So, what else we're going to talk about? Oh, I did some price comparisons. 1-inch diameter Garolite Triple X, Garolite, Garolite, also known as Bakelite. I like the term Bakelite. It just sounds like an edible good, like a food item. So we don't do that. We don't eat rockets. We don't eat rocket fuel here. Garolite Triple X. There's 3 X's, not 2. Is obviously a lot stronger. It's more expensive. 24-inch length, 1 inch in diameter, with 1/16 wall thickness. I believe if this is amazing, if it's available in that 1/8 wall thickness. So it's a 3/4 inch inner diameter. So it's basically similar in dimensions to Schedule 40 PVC. I'm guessing of the same outer diameter. But 24-inch section with 1/4 inch wall, no, 1/8 wall thickness makes a total of 1/4 inch, at least 3/4 in the inner diameter, 1 inch tube. Garolite Triple X, 24 inches in length, outer diameter being 1 inch. It's going to set you back, get this, $36 and change with shipping. Probably looking around $42. One 1-inch, 24 inch length, transversely 1 inch across, 1/8 walls. The stuff is be kick-ass material for some really strong rocket fuel like potassium, ammonium perchlorate, aluminum, little iron oxide to control the burn rate, and epoxy. I think there was some other additives. AP fuel, basically the same solid rocket fuel formula is that the Morton used to make the propellant for the space shuttle boosters. There you go. But you know what? It's a long way around. It's low yield. I found I have more. In my opinion, I had better performance out of ammonium nitrate, magnesium, and just a little bit of epoxy. And I think my ammonium nitrate, magnesium, epoxy motors could kick an AP motor's ass any day of the week. I said ass the second time, that's the third time. I promise I wouldn't cuss. Why did I mention that? Well, here we go, folks. In keeping the cost of the rocket motors fuels down, and that's one thing, but in designing these single-use rocket motor cartridges, you have to consider the thermal value properties of individual propellants times the desired diameter of the nozzle itself, the nozzle throat, and of course the things like the weight of the rocket, coefficient of drag, what you're going to be doing with the rocket. I don't want to know. But if I do find out, like I said, I'll shut the channel down and have all these episodes erased by YouTube. But when considering the sleeving material, I'm going to try Garolite Double F with a 1/16 wall thickness, which is a total of 1/8 underneath the diameter, the outer diameter of the Garolite tubing itself. The only problem with that is the Garolite tubing. If I'm saying it's 1 inch and I'm assuming the motor tubes are 1 inch, then I've got to remove the material, so I have to go with thicker, greater wall thickness. So I don't know, but I'm gonna have to do my research. But I just wanted to let you know general prices. Garolite double X is gonna cost X amount of dollars, and Garolite triple X, which is high end stuff, it's gonna cost you about roughly 50% more. And if anybody finds out I'm using these materials for aerospace application, guess what? All of a sudden, all the other rocket builders are gonna get a great idea from me, steal it, and suddenly that stuff will be unavailable on the internet. That's happened on, oh my goodness, I want to say about 4 or 5 different occasions. It's not the government; it's these individual companies. They watch infomercials like this, or they consider them infomercials, and they steal my ideas. I'm flattered, but you know, at some point in time, that's going to get a little on the tiring side. Anyway, so that's that. We've talked quite a bit. I told you what else I'm going to do. Um, so I'm going to put the section of this back. I am happy about how they evened out. I know I only do so much for each episode, but again, there's a lot to talk about when it comes to rocketry. And of course, I know I'm in for a long battle. I really want to machine down that coupling and get this upper section in. And later on today, in addition to machining down that coupling, I'm going to be working on some type of modified wood lathe, because the thing is about these model rocket nose cones, I have to fabricate a model rocket nose cone. I'll show you how to do that, but I have to make a decision as to whether the fabricated nose cone is a plug for a mold maker, or if I'm actually going to use the actual method for manufacturing a nose cone on the end of this rocket, because they're going to be so heavy and somebody needs to balance out their complex rocket like this one that way. So I don't know what to do. So I have to make an engineering decision on that as well. However, again, as I mentioned, when you leave comments, I really need somebody to start leaving some comments. I appreciate the compliments, but they don't, I don't mean to be thankless or rude. They don't really do me any good. What I need is criticism, and criticism in the form of constructive criticism, in the form of some helpful input. That I know there are some things that I'm doing that's wrong. I mean, not immoral, illegal, or fattening, but just outright dangerous or overly time consuming. Um, Another thing I mentioned before about aerospace, the biggest expense in aerospace isn't the government licensing or regulation. You get plenty of money from the government in the way of grant research funds and manufacturing funds and stimuluses and so forth. The biggest expense in aerospace is always the labor. And if I had more people helping me with this rocket, say if I had Ulysses Andradas helping me, if he could follow, I'd have him follow instructions on what needs to be done. There's a couple other people who'd like to be mechanical engineers working on rockets. I've lost their phone numbers. When I get the resources, believe you me, this is going to become a team sport. Even the single engine student rockets, I'm going to need some help. I'm going to need somebody with a pointer to help me with lab. I'm going to need somebody to help me with production value. So somebody who wants to make very, very capable, good looking news commentary. So that's called production value. I need to work on my website, and I need to work on my weight. I gotta tell you guys, I see myself on camera. I don't care what anybody says. I'm a friendly, nice, kind person. Maybe I have a good speech quality. Maybe I don't. But what I don't like is looking at my paunch. I need to lose about 40 pounds. It's not just to look good in front of other people. It's for my own sense of self-worth. And it's important. It's important to look your best on TV, on the internet, or on the internet. It's important to look reasonably decent enough. And I can't, with 40 or 50 or even 60 pounds of extra weight. I'm at 245 pounds right now. My ideal weight is 175. So 25 plus 45, that equals 70 pounds, so it's not fun. I just want to let you know, so between losing weight and the website being information and knowledge portal, and I'll be selling some rockets on that, rockets designs that are tested, and getting this website or this area of technology, excuse me, getting this show monetized, so I have to work on that. So getting the show monetized, getting the website up, building these rockets, getting to the point where we can actually launch them, and making launch equipment, which is something I'm going to start on as well, but I'm going to do that tomorrow because I got to get this nose cone business figured out, and I got that coupler taken care of. I have to leave to do some errands right now, so I got to get that all figured out. So nose cone and coupler today. We'll figure that out. I'll let you know my decision on the nose cones tomorrow. I have a couple of leads for people who can make molds for me. That might be better that way, and to just add counterweights or clay. But I'll let you know about my decision about that. But tomorrow, what you guys have to look for tomorrow's lab and lecture, you're absolutely, positively I'm going to inform you on my decision as far as the nose cones are concerned. That's number one, and we're going to figure out whether or not we want to subcontract and let a guy go ahead and mold nose cones, or if we just grin and bear it and just fabricate the nose cones the old-fashioned way, the way I do it, which is very time-consuming. So we'll make that decision, and then we're going to go ahead and get on installing the coupler as well. And I'm going to stay on this rocket for a while. The center section is going to be a spool section. We're going to use some heavy-duty plastic. I got some really, really, really nice gray-brown plastic that's nearly an eighth of an inch thick, and it was like it's like a 36 by 24 sheet, eighth of an inch thick. Really, really super, super ultra high quality gray PVC with a little bit of impact approved or impact resistant qualities in it, like mixed with mixed with some polycarbonate qualities. For all I know, this piece cost me. For all I know, could have some polycarbonate in it. So, a gray non-translucent polycarbonate, 1/8 of an inch thick. I kind of want to show it to you right now, but you know what? I think I will. Let's just go ahead and do that. So I'm going to set this aside on the bed, disrupt the kitty's plans for taking a nap. Haha. I'll put my glasses back on. Where is the coupler? I'm not going to clean up this table because I'm going to machining that down, fitting and gluing on that. And then I'll do that and that. I'm going to start on the nose cone tonight, make a decision about that. Then tomorrow, I'll tell you about the decision for the nose cone. And I'll tell you about setting up a payload spool plus a couple of anchor spools, and what we're using this gray plastic material for. Let me set it like that. And rocket's already a little flimsy in the middle, but it launches vertically, not horizontally. And this is it. And I'm looking at this stuff, and I got to tell you, one thing I have to say about American plastics. American plastics are absolutely, positively, bar none, in their quality. It never ceases to amaze me. American steel, American fiberglass, American plastic, American textiles, American denim, American aluminum, American materials, American raw materials. They're just absolutely positively second to none. And in my opinion, American raw materials are even better than what you can get from either Germany or Denmark. Although the Garolite double and triple F tubing that I was talking to you about, available on McMaster-Carr, that does come from Denmark. So in that sense, but Denmark, some materials from the United Kingdom, some textiles from India, some materials from Japan are good, but American raw materials are just the best. I think it's because this country's been doing it for so long, we've refined the process, and they're able to get what the materials are worth and such and so forth. But this is a material that I'm going to be using for not the nose cones, because, well, you know what? Hold on. Yes, okay, so the decision is I'm going to be using this material for the nose cones, but I'm also going to be using this material for the bulkhead rings, for the electronics bay spools and the anchor spools for the recovery system. So this twin engine rocket is in fact turning out to be a complex rocket. Sorry, I couldn't help myself. Can't keep a good rocket down. Okay, so look forward to tomorrow. I'll tell you the decision about the rocket nose cones, whether we're going to go with fabricated nose cone or if I've made a nose cone plug, and we're going to go with molded nose cones, custom molded nose cones. So we'll make that decision tomorrow, and then we're going to go ahead and do the anchor spools and the payload base spools using this material. The day following, I'm going to go ahead and share with you the details of a launch unit, and I'm also I may end up making this one a little on the complex side. I might just end up using an internal battery and charger for this as well, instead